So hello everyone, this is lecture 10 for the classical physics. In the last lecture we discussed about the law of orbits for the Kepler's law, and we derived the energy for the elliptical orbit and the circular orbit. We described about the eccentricity and all, and how it defines the orbit. So today we will see the other two laws, that are law of areas. You already see this law. We already proved that aerial velocity of a planet or anything moving around, revolving around a sun will be constant. Means Kepler's law is particular for the planetary system. So that's why radius vector from the sun to the planet sweeps equal area in equal interval of time, and this is our law of areas. And law of period is nothing but square of period of revolution of the planet about the sun is proportional to the cube of the sine major axis. So if this is ellipse, sine major axis is a from sun to this aphelion, means not sun, means this hole is 2a, so half will be semi major axis, and time period will be the time period of whole revolution is this. So square of this is proportional to aq. So if there is two planets and this is sun, so for this relation valid, and for other two planets and other planets this relation is also valid. So we can find this relation between these two different planets, and we can find any variable by giving other three. So remember these are very important relations. Now let's see some questions based on these Kepler's law. So an interstellar object has speed v at the point of shortest distance r from a star of much larger mass m. Given this, v square is 2gm over r, this is r speed. So trajectory of the object is, so we need to find the orbit, what kind of orbit it will have. So interstellar object has a speed v at the point of shortest distance. So shortest distance will be r perihelion, that is r. So we know about the energy, so let's find the energy of that particle or that object. So energy is nothing but half mr dot square plus l square over 2 mr square vr. This is effective potential and this is our radial kinetic energy. So we know for the elliptical orbit or any kind of orbit it will be, if at the shortest and the minimum distance we have this radial component is 0, because these are the turning points. So this will turn out to be 0 at shortest distance capital R. So this will be 0. Now in place of R we will have capital R square, and it will be V capital R. So now energy will be this. So from this equation we can see this potential for a planet. We know this is minus gmm over r, we already know this expression. And this L is nothing but at the shortest distance it is mvr, simple, means the moment of linear momentum, means r cross p. So r is r and p is mv, so mvr. So this will be our L, so m square v square r square, this will be our expression. Now in place of v square substitute this value, 2gm over r. So you will get this value, and after solving this you will get 0, because this is also gmm over r, this is minus gmm over r, so 0. So energy, total energy of the particle came out to be 0. So what kind of conclusion we can draw? So we already seen the energy for different kind of orbits. So if it is 0, then it can't be a bound orbit. Okay, means it can't be ellipse, it can't be a circular, it should be unbound. And it is 0, then it should be parabola, because we already see this. Remember this table always. For e equal to 0 we will have parabola, for e greater than 0 we will have hyperbola, and all these expressions. This is very important. So from here we can find this conclusion that the orbit of the particle will be parabola. Now let's see one more question. A particle of mass m moves in a central potential this vr minus k over r in an elliptical orbit. So equation of orbit is given, r theta equal to a 1 minus e square divided by 1 plus e cos theta, where theta is greater than 0, less than 2 pi, and a and e denotes the semi major axis and e denotes the eccentricity respectively. If its energy is minus k over 2a, so maximum kinetic energy is. So we need to find the maximum kinetic energy, and energy is given. So energy is minus k over 2a. So from this expression we know it is definitely be ellipse. Okay. So kinetic energy is total energy minus potential energy, and total energy is given minus k over 2a plus k over r. This is our potential, we know this is also given. Now find the, means put the, substitute the value for r. R is nothing but this, so we'll get this value. Now this expression we have, now we need to find the maximum value of this. So this will be maximum when this, and see the only variable in whole this equation is theta, all are constants. So when this value is maximum, then this whole term will be maximum, because this will be in plus nature. So this will be maximum when cos theta is 1, maximum value of cos theta is 1 only. So let's put cos theta equal to 1, we will get 1 plus e, 1 minus e square. here it will be 1 plus e 1 minus e, so 1 plus e will cancel out, we will get 1 minus e only. So now take the k by 2a common, minus k by 2a, we will get 1 minus 2 over 1 minus epsilon, means not epsilon, it is e. So now this k over 2a, sorry, this minus k over 2a is total energy E, and here we will see 1 minus E minus 2 will give us minus 1 plus E over 1 minus E. This can be written this. So maximum kinetic energy will be this. So this was the option in the options. So that's why we rearrange this form to this form. Okay, so this is your answer. This is maximum kinetic energy. Let's see one more question. The circular and parabolic orbits in an attractive potential given as this. So potential given as, in this potential there is circular and parabolic orbit is possible, so has same value of angular momentum. So for this potential they have same value of angular momentum. Now if rp is the distance of perihelion distance of parabola, perihelion means the minimum distance, and rc is the radius of the circle, so we need to find this ratio rc over rp. So we know from the formula we derived for the r theta, that was L square over mk 1 plus epsilon cos theta. This epsilon denotes the eccentricity. So for circular orbits we know epsilon is 0, we as you saw in the table, so we'll substitute 0 here, so we'll get r theta equal to L square over mk. This is for circular. So now we have radius for circular orbit, this will be L square over mk. Now to find this ratio we need to find rp. So for rp we know this epsilon is 1 for the parabolic path, so we'll get L square over mk divided by 1 plus cos theta, this will be 1. Now see, perihelion is minimum distance. Okay, so to minimize this whole value we need to maximize this denominator, so it will be maximized when cos theta will be 1. So you substitute 1 here, so it will be 1 plus 1 2, so r parabolic will be L square over mk divided by 2, so this will be this. Now you can find this ratio rc divided by rp, you will get 2 as your answer. Let's see one more question. A satellite of mass m is an elliptic orbit about Earth, means satellite is moving in an elliptical orbit about Earth. At the perigee, means that the minimum distance, it has altitude of 1100 km, and at the apogee, means at the maximum distance, its altitude is 4100 km. If radius of the Earth is 6400 km, then we need to find the eccentricity. So here we will use this formula. We already derived this when we are talking about the eccentricity. So see, if this is your Earth, then that satellite is moving like this. So at the perihelion, means the minimum distance, this distance is 1100 km and this is radius, and at the maximum distance like this, we will have this distance as our maximum distance, apogee. So this r max will be this capital R plus this 4100 km, and at this point, perihelion point, we will have this r min as r plus h. So just add these values, means radius is given 6400 and maximum is this, so this will be our r max, and adding this with this will give us r min. So substitute here and you will get the eccentricity as 0.16. Now let's see one more question. Assume that Earth revolves in a circular orbit around a sun. Earth is revolving around a sun in a circular orbit, so it is given that it is circular, not elliptical. Suppose the gravitational constant g varies slowly as function of time. So it is given that g is varying with time, and in particular it decreases to its half of its initial value in the course of 1 million years. In 1 million years, this g becomes half of its value, g by 2, during this 1 million year. So we need to see which conclusion is right. So radius of Earth's orbit increases by factor 2, or total energy of the Earth remain constant, orbital angular momentum of Earth will increase, radius of the Earth's orbit will remain same. So let's see one by one. First, the planet is revolving. Okay, so it is g is decreasing. So if 1 million years, after the 1 million years, we see that there is no external torque applied to this planet. Okay, in whole this process no external force was there, so this torque will be 0, and this will give us angular momentum as constant, means dl over dt is nothing but torque. So this is 0, so L will be constant. So we will say that orbital angular momentum of Earth will increase. So this option is incorrect because angular momentum will remain same. So this is wrong. Now let's see energy. So energy is half mr dot square plus L square over 2mr square minus, this is our potential. Now see, this is a function of time, so this whole value will change with time. So we'll say that energy is not constant again. So total energy of the earth remain constant. This option is also wrong. Now let's see about the radius. It is given that it is circular orbit, so we can find the circular radius. Radius, how can you find? You take this V effective potential and differentiate with respect to r and put it equal to 0. That's how you can find the r naught radius. So let's see. So after solving this, we will get this, and the relation between r and gt will be this, because other terms are constant, so r will be inversely proportional to gt. So this will give us the relation r1 g1 equal to r2 g2, because this is like this. So we'll get this relation r2 g2 equal to r1 g1. So we can see that for the means radius is not constant definitely. So this option is also incorrect. Radius of the earth orbit will remain same. This will not remain same because it is varying inversely as gt. Now this option is incorrect, so only option remaining is 1. So radius of earth's orbit increased by factor 2. So this will be right. Let's see if it is 2 or not. So this is our relation. So g2 is nothing but g1 by 2. So it will give us g1 over 2. G1 will cancel out, it will give us 2. So r2 is nothing but 2r1. So it will increase by a factor of 2. So 2 into r1 is r2. So option is correct. Now I gave you these two questions. I will give you these two questions. Try to solve these. This is a complete exercise to get whole idea about the central forces. In the next lecture, we will discuss the solution. So for now, you will try to solve these questions by yourself. A particle of mass 1 kg, angular momentum L is given, root 2 kg meter square per second, and total energy E is equal to 3 joule, is subjected to a central force field, that is F equal to minus kr, where k is 2 kg per second square. Which of the following statement is true? The centers of all the circles in the options below are at origin. So option A is particle is constrained to be in the region outside the circle with radius r equal to under root 3 plus root 5 divided by 2. B option is particle is bound within the annular region. Annular region nothing but if there are two circles, then this region is called the annular region. So particle is bound within annular region described by the two circles with radius r1 is equal to this 5 minus root 3 by 2, or r2 is 5 plus root 3 by 2. Or option 3, the particle is bound within the annular region described by two particles. These radius will be in the C option. So in D option, particle is constrained to be in the region outside the circle with radius 5 plus root 3 by 2. So option C will be correct. Now try to solve this question by yourself. In the next lecture, we will see the solution. So there is one more question you will try by yourself. A particle of unit mass move in a potential Vr equal to minus V naught exponential minus r square. If the angular momentum of the particle is this, L equal to 0.5 under root V naught, which of the statements are true? There are two equilibrium points along the radial coordinates. There is one stable equilibrium point at r1 and one unstable equilibrium point at r2 greater than r1. There are two stable equilibrium along radial coordinates. There is only one equilibrium point along the radial vector. So B option will be right. Try to solve it by yourself. If you try by yourself, then your many doubts will be clear and many concepts will be at good terms for you. So try to solve them. We will see the solution in the next lecture. Thank you everyone.